As we mentioned before, one of the tools in our CIA toolbox, confidentiality, integrity, and availability, is Owasp, the Open Web Application Security Project. So in this module, we're going to introduce Owasp. We'll look at several of the Owasp top 10 mobile security risks and get you in the habit of visiting and referring to the Owasp website and other external resources for reference. So Owasp originated as the Web Application Security Project, but as internet applications have moved into the handheld, the Owasp has broadened its scope and now produces work also centered on mobile applications. The top 10 is their list of the top 10 categories of vulnerabilities, both for web applications or for mobile applications. This is a standardized way for you to refer to these type of vulnerabilities or classes of vulnerabilities, to study them and hopefully to avoid them. This is a particular representation of the Owasp top 10. Don't focus on the numbers. These change as the Owasp top 10 is revised periodically. Refer to the Owasp website, owasp.org, and study the top 10. So let's look at a few of the Owasp top 10 for mobile. Number one on the list for our consideration is insecure storage. Now this is a consideration for mobile for two reasons. First of all, many applications store data locally on the handheld for performance reasons or for reference when the mobile data connection is not available. How is that data secured? How is that data at rest secured? Is it encrypted? Is it stored to secure storage? Is it stored to removable memory? We don't know. These are all things that the designer and the programmer must consider. Secondarily, these devices are different than traditional computing in that they are mobile, small, and easily lost or stolen. So you must always assume the attacker will have physical access to the device and be able to access the data. How do we secure it against that access? Now let's consider a common programming flaw which leads to a buffer overflow vulnerability. So examine the code snippets here on the left and the right. And on the left you'll see that we allocate a variable. We'll call it text, and we set its size to 100 characters. Then, with the printf statement, we prompt the user to enter some text. And then on the third line, we use the scanf function to read in what the user enters and push it into the variable text. But what happens if the user enters more than 100 characters? Unpredictable, isn't it? So a better way to perform this same function is to allocate the variable text 100 characters, prompt the user as we did before, but now we use a different parameter for scanf and we read in 99 characters only, not 100, because we allow for one additional character for the null termination, and that's what we load into the variable. So now we know that we have loaded 100 bytes into a 100 byte buffer. There's no opportunity to overflow that buffer. In the first example, if an attacker inserts malicious code at the end of his input and he works with this over and over and over, he can locate that code arbitrarily in your program memory, cause you to execute it, and gain control of your program. This is called a buffer overflow. Improper session handling is another common flaw with mobile applications. Remember, we establish a session between our handheld and the server on the back end. But the handheld is by definition mobile. It will roam from one network to another. It will move from the cellular data network to the Wi-Fi network. How do we handle those sessions and maintain a knowledge of which user is connected to which data set on the back end? There are lots of ways to get this wrong. Study the Owasp top 10 for improper session handling and understand how to get it right. It's inappropriate to make security decisions via untrusted inputs. And by definition, everything that comes from our handheld is untrusted because we don't know with certainty that it hasn't fallen into the hands of a malicious user. Validate your inputs. Don't make security decisions without clearly identifying the user, authenticating who they are, and validating the input. SideChannel data leakage is another interesting problem, particularly with the iOS on the Apple platform. Consider a common usage scenario. You're doing something with your phone and the phone rings. Now what happens? You get a pop-up message that says, would you like to answer the phone call? If you say yes, the application you were using goes into the background. You make the call, you finish, you hit the end, and the application comes back up. Now, if you notice, when the application comes back to the foreground, if you start to interact with it immediately, it's not always responsive. Why not? Because what iOS does is take a snapshot of the screen of your application when it puts it in the background. And then when it moves it back into the foreground after your call is ended, it immediately displays that snapshot photo while the memory is being manipulated to move the application into active memory. So ask yourself, were you doing something sensitive with the application? Perhaps entering a logon, password, or other sensitive data that was then captured by that screenshot? Where is that screenshot stored? In secure memory, encrypted, or in plain memory? How is it destroyed? How is it cleared? These are all things that must be considered by the application programmer to prevent side-channel data leakage. So the objective here was to introduce the Owasp, the Open Web Application Security Project, and to get you in the habit of visiting the Owasp website and other external resources for references in this highly complex topic. Thank you.